Do you struggle with series and parallel resistance problems like this one? Everything looks simple at first, but the final answer just doesn't match. If this has ever confused you, don't worry. In the next 6 minutes, this video will make everything crystal clear. Hello and welcome back to the Current Electricity series. This is video 2, and today we will address the root cause behind most mistakes in resistance problems. That root cause is Ohm's law. Ohm's law states that the electric current through a conductor between any 2 points is directly proportional to the voltage applied across those 2 points, provided the physical conditions of the conductor remain the same. The constant of proportionality between voltage and current is called the resistance. Instead of memorizing this statement, let us understand Ohm's law using simple real-life analogies. We will first understand the analogy for voltage and current, and then we will understand resistance. Consider that you are driving a car on a highway. When you press the accelerator lightly, for example at 10% throttle, the car moves slowly. When you press the accelerator harder, the speed of the car increases. In this analogy, pressing the accelerator is equivalent to increasing the voltage, and the speed of the car is equivalent to the electric current flowing through a circuit. Now let us look at resistance in the same example. The friction between the car's tires and the road resists the motion of the car. This friction is equivalent to electrical resistance in a conductor. A smooth road offers less resistance, while a rough road offers more resistance. Now consider a situation where resistance increases. You are driving the car at the same 10% throttle, but you reach an uphill road. If you do not increase the throttle, the car slows down. To maintain the same speed, you must press the accelerator harder. Here, the uphill road represents an increase in resistance. Increasing the throttle represents an increase in voltage. Maintaining the same speed represents maintaining the same current. This tells us that when resistance increases, a higher voltage is required to maintain the same current. Let us now look at another familiar example, the water tank. The flow of water through the outlet pipe of a tank depends on the height of water above the ground. A higher water level produces a higher water flow. In this analogy, the height of the water tank represents voltage, and the water flow rate represents electric current. Now, if we reduce the diameter of the outlet pipe, the water flow decreases even though the water level remains the same. Reducing the pipe diameter represents an increase in resistance, and the reduced water flow represents a decrease in current for the same voltage. Finally, let us apply this understanding to an electrical circuit. Consider a simple circuit with a battery and a wire. If the battery voltage is 1 volt and the current flowing through the wire is 1 ampere, then increasing the battery voltage to 2 volts will increase the current through the same wire to 2 amperes. This shows that the current flowing through a conductor is directly proportional to the applied voltage, as long as the resistance remains constant. This relationship between voltage, current, and resistance is known as Ohm's law. Now that we clearly understand Ohm's law, let us move on to series and parallel connection of resistors. First, let us define these connections. When resistors are connected end-to-end so that the same current flows through each resistor, this type of connection is called a series connection. When resistors are connected between the same 2 nodes, such that the voltage across each resistor is the same, this type of connection is called a parallel connection. Now let us talk about effective resistance. For a series connection, the effective resistance is simply equal to the sum of individual resistances. For a parallel connection, the reciprocal of the effective resistance is equal to the sum of the reciprocals of the individual resistances. Instead of treating this as a purely mathematical rule, let us understand the physical meaning behind it using fluid flow. We all know that resistance to the flow of water is higher in a narrow pipe compared to a wider pipe. Now consider 2 tall water tanks. One tank is filled with water and the other tank is empty. Suppose we connect these 2 tanks using a single large pipe with a diameter of 200 centimeters. Because the pipe is wide, water flows easily and the flow rate is high. Now let us introduce another pipe with a smaller diameter of 50 centimeters and observe what happens when we add it to the system. First, consider adding the smaller pipe in series with the larger pipe. When pipes are connected in series, the water must pass through both pipes one after the other. The narrow pipe increases the difficulty for water to flow, so the resistance of the smaller pipe adds to the resistance of the larger pipe, and the overall water flow reduces. This is exactly what happens in a series electrical circuit. Resistances add up and make it harder for current to flow. Now let us consider the second case, where we add the smaller pipe in parallel with the larger pipe. In this case, water now has multiple paths to flow from one tank to the other. Even though one pipe is narrow, it still allows additional flow. As a result, the total water flow increases. This means that in a parallel connection, we are adding the flow carrying capability of each pipe. In electrical terms, we are adding conductance, not resistance. Conductance is simply the reciprocal of resistance. That is why in parallel circuits, the reciprocals of resistances add, and the effective resistance decreases. This behavior is not mathematical magic. It is physically intuitive once we understand how current prefers multiple paths. Now finally, as promised at the beginning of the video, we will solve the circuit step by step. I strongly recommend that you pause the video and fully understand the first two steps. Once these two steps are clear, the rest of the circuit will get solved automatically in a cascade manner using the same ideas. Let's start from R8 and R10. These two are in series. The equivalent resistance will be sum of these two resistances. Let the equivalent resistance be R1 prime. R1 prime will be 12 ohms. Now R1 prime and R9 are in parallel. The equivalent resistance will be calculated as shown. Let the equivalent resistance be R2 prime. R2 prime will be 4 ohms. Now R2 prime and R7 are in series. The equivalent resistance will be sum of these two resistances. Let the equivalent resistance be R3 prime. R3 prime will be 12 ohms. Next, R3 prime and R6 are in parallel. The equivalent resistance will be calculated as shown. Let the equivalent resistance be R4 prime. R4 prime will be 4 ohms. Then R4 prime and R5 are in series. The equivalent resistance will be the sum of these two resistances. Let the equivalent resistance be R5 prime. R5 prime will be 8 ohms. Then again, R5 prime and R4 are in parallel. The equivalent resistance will be calculated as shown. Let the equivalent resistance be R6 prime. R6 prime will be 4 ohms. Again, R6 prime and R3 are in series. The equivalent resistance will be the sum of these two resistances. Let the equivalent resistance be R7 prime. R7 will be 8 ohms. Now R7 and R2 are in parallel. The equivalent resistance will be calculated as shown. Let the equivalent resistance be R8 prime. R8 prime will be 4 ohms. Finally, R8 prime and R1 are in series. The equivalent resistance will be the sum of these two resistances. Let the equivalent resistance be R9 prime. R9 will be 10 ohms. Thank you for watching this video and for spending your valuable time here. In the next video, we will discuss Kirchhoff's current law and Kirchhoff's voltage law in detail. If you found this video helpful, please like, share, and subscribe to the channel, and don't forget to press the bell icon to stay updated.